So the topic that we are going to talk about today is shear flow in closed cross-section thin wall beams. So we have done similar problems but for open cross-section thin wall beam, like the beam having an I cross-section or a C cross-section, and likewise. So as I have said at the end of the last lecture, that the problem with closed cross-section beam, finding out the shear flow in closed cross-section beam due to shear force, sorry I missed it, okay, due to shear force is that there is no open edge or free edge for which I can consider Q0 to be equal to 0. Okay, so there is no such free edge in a closed cross section beam for which I can find out Q0 for which Q0 is equal to 0. So I will have an unknown Q0 hanging with me throughout the calculation or analysis, and I will not be able to find out the value of Q0 unless I use some additional information. Okay, so with this, let me draw a closed cross section beam and see what would be the case. So suppose this is a closed cross section thin wall beam. Sorry. So maybe the thickness is T, which could be a function of S. Okay, so this is the thickness. Now let me even draw the axis. So this is the x-axis, this is the y-axis. So now so QS is going to be the force, QS is going to be the shear flow which can be obtained by solving this equation, right? So QS would be achievable by solving this equation. So as I said, Q0 is going to be the only problem. So what I do for that case is that I imagine a slit, I consider that sorry for the last statement, so not a state. So I consider an arbitrary point on the cross section, on the thin wall of the cross section, for which I assume that the shear flow at that point is Q0. I just make this assumption. Okay, so once I make this assumption, or once I consider that the shear flow at an arbitrary point on the cross section is Q0. So let me write down shear flow on an arbitrary point on the cross section is considered to be Q0. Okay, is considered as Q0. Now once I do this, then probably I can solve the equation 1. I can solve equation 1, and the entire solution of QS will be known with an unknown term Q0. Okay, right? So this things of course is going to get much clearer as we solve certain example. But I think you can appreciate this, that I will by solving equation 1 using the sectional properties, I can easily find out QS, or the shear flow as a function of S over the cross section of the beam. But there would be in that solution for QS, there would be an unknown Q0 lying there, which I need to find out. So how would I find out? So then what I say is that for Sx Okay, so can you think of the answer of this question? So let us consider that the applied shear force Sx and Sy are passing through the shear center of the cross section. So if that is the case, what do you think would be the integral tau ds going to be? Okay, so you have to remember the Bredt-Batho's theorem, and what do you think that tau ds is going to be? Okay, so what is, by Bredt-Batho's theorem, what is tau ds? So we have applied Bredt-Batho's theorem for torsional moment. Okay, so now understand this, that Sx and Sy are passing through shear center, so they are not going to produce any torsional moment. So the shear flow that is going to develop in the cross section because of Sx and Sy are entirely due to the shear force, and there is no torsional moment component into it. Therefore tau ds is going to be equal to 0, which is basically 2g a theta. I will write it this way. So 2g a theta, and theta, which is the rate of twist, is equal to 0 as Sx and Sy passes through the centroid. Passes through the shear center. Right? So therefore tau ds is going to be equal to 0. So this can further be written as, in place of tau, let me write this as qs by ts into ds, because we are usually finding out shear flow and not shear stress. So from this equation I can write qs by ts is integral of qs by ts over ds is going to be 0. So this is the additional equation, which along with equation 2 is going to give me the value of q0. So what am I going to do? From equation 1, I am going to find out the expression for qs, which will of course have an unknown term q0. Now that qs I am going to integrate following the expression given by equation 2. If I evaluate that integral, I will get an expression in terms of q0, and by equating that expression to 0, I will get a value of q0. So equations 1 and 2 are going to give the solution for qs. Okay, so that is the overall idea, right? So let me solve an example, and this will be furthermore clear if we solve this example. So let me draw the Okay, so the problem states that I have this rectangular thin wall cross section beam, okay, and the externally applied shear forces that act on the beam are Sy, which is equal to F, and the shear force in x direction is 0, and this shear force Sy is acting through the shear center of the cross section. Okay. The centroidal location of the cross section is given, which is 26T from the left hand side center line of the left hand side leg or portion, and 34 from the right hand side leg or portion. The dimensions are 60T by 48T. The thickness is varying, and I have shown the thicknesses. So the cross section is symmetric about x axis. Okay, so the cross section, as you can see, is symmetric about x axis. And therefore, since it has a symmetry, Ixy is equal to 0 for the cross section. So therefore my Qs minus Q0 for this cross section is going to be minus Sx, is going to be Sy by Ixx into 0 to S dy ds. Okay, where Ixx, so I need to find out only Ixx, so I can very easily find it out. Okay, so it is for the top and bottom flanges, this is going to be 2 into 60T into T into 24T whole square plus 1 by 12 48T whole cube into 3T plus 1 by 12 into T. Okay, that is what into 2T, sorry, into into 2T, which if I calculate correctly, I'm going to get it as 115,200 T to the power 4. So this is the value of Ixx. Okay, so now my so I have got the expression. So Sy indeed can be replaced by F, because Sy is F. So now let me try to find out the value of Qs over the cross section. Okay, let me number the points. Okay, so let me call this as point 1, this as point 2, this as point 3, and this as point 4. Okay, so let me assume that the shear flow at point 1 Q1 is equal to Q0, and let us start finding out the calculations for it. Okay, now for flange 1 2, so let us start with for flange 1 2. Okay, so for flange 1 2, as we did in the case of open cross section beam, I can write, so for flange 1 2, let us see, S is going to lie between, S is going to lie between 60T and 0. Okay, and y is going to be 24t. Okay, so let me call this as equation 1. So I have to plug this in equation 1. So I will get q12s minus q0 is going to be f, thickness is t of course, so ixx into y is 24t, so I have 24t square into s. Okay, therefore q12s is going to be equal to q0 plus f into 24t square s by ixx. Okay, so this is my second equation. So from this equation I can get q2 is going to be at s equals to 60t. So that is going to be q0 plus f into 24 t square into 60t by ixx. So if I evaluate that, that is going to be q0 plus 1440 tq plus f by ixx into 1440 into tq. Okay, so I get the value of q2 and q12s. Okay, now let me clear the, so keeping this, let me clear the entire canvas. Okay, and let me just carry this here, saying that one thing that I have to carry is qs minus q0 is f by ixx dy dx. That is equation 1 that I have to carry. Equation 2 is q12s is equal to q0 plus f 24 t square s. Okay, so this is my equation 2. So I can erase this off further. So this part is done. So this entirely makes an expression. Okay, so now, so let me find out for the next. So for web 2 3, let me see. So it is going to be q23s minus q2 is going to be f by ixx and t into y ds. So that is going to be f by ixx. T here is 3t, so I can take 3t out, and y, so s is between 48t and 0, and y is going to be minus s plus 24t, right? So I have, in place of y, I can write this as minus s plus 24t into ds. Okay, so if I evaluate this, q23s is going to be q2 plus f 3t . 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 Okay, so now so this is the expression 3. So now let me see what is Q3. Q3 is Q23 at S equals to 48T. So that is going to be Q2 plus, so S square at 48 is, this is 24 into 48, and this is also 24 into 48. So this is going to go to 0. So I will have this as Q2. Okay, so let me also write this down. So let me just erase this off, and okay, so Q23 S is therefore Q2 plus F by Ixx. In place F by Ixx into 24 minus S square by 2 plus 24 TS, and Q3 is going to be Q2. Okay, so this is another expression, and I call it as 3. Now let me find out for flange 3, 4. Okay, where S is going to 60T, so Q34S minus Q3 is going to be F by now Q3 we have found out to be Q2. So Q3 is Q2. So so this is going to be Q2 minus so Q4 therefore is Q34 at S equals to 60T, and that is going to be Q2 minus in place of Q2 I can write this as Q0 plus F of Ixx 1440 T square minus F of Ixx 1440 T square. Okay, so this is going to cancel out, so my Q4 is going to be equal to Q0, right? So I will again write this here. So Q34S is going to be Q2 and Q4 is going to be Q0. So this is my fourth equation. Let me mark it and erase the rest of the expression. Okay, so now I have got Q34, so the last leg is left. So for web 4, 1, For wave 4-1, S is again between 48t to 0 and y is equal to S minus 24t. Because at S equal to 0, y is minus 24t, and at S equals to 48, y is equal to 24t. So this is correct. Okay, so let me write Q41S minus Q4 is going to be F by Ixx into T is going to be 2T, and so 0 to S minus 24T into ds. Okay, so Q41S is going to be Q4 plus F by Ixx 2T S square minus 24TS. Okay, so Q4 is Q0. So I have this as Q0 plus F by Ixx 2T S square 2 minus 24TS. Okay, so let me see what is Q1. Q1 is Q41 at S equals to 48T, and that is going to be equal to Q0. So this, because this part is 0 at S equals to 48T. Okay, so right, so this goes to 0. So I have Q1 which is equal to Q0. So this is an important check. Okay, so this is a good check, because I have started with Q1 equals to Q0, right, and eventually after going through the entire cross section, I am again being able to find out that Q1 equals to Q0. So that is a check to see that all the calculations that you have done before this to arrive at this point is correct. Okay, so therefore I can write Q41 S as Q0 plus into S square by 2 S, and Q1 is equal to Q0. So this is my equation 5, and let me highlight this. Okay, so right, so this is going to be fine. I'm just checking Q23 must be having a 3T somewhere. Yes, so this should be, I have missed a 3T here. So this is going to be a 3T here, sir. So this is going to be 3T. Okay, so now I have, so what I have done is that I have found out the shear flow in all entire cross section, and the only unknown left with me is Q0. Okay, so now I will use the expression that if F is passing through the shear center, as is the case for this problem, then I can say Qs by Ts into ds has to be equal to 0. Okay, so from all this expression that we have derived from equation 2 to 5, so let me call this as equation 6. Okay, so using equations 2 to 5 in equation 6, we will get the value of q0. So let us see how we are going to evaluate this integral. So I have to divide the integral because t is not entirely uniform through the cross section. So t is constant over each portion of the leg, but it is not constant throughout. So I have and also qs is not a single function throughout the cross section. So the integral given by equation 6 has to be written in this way. So it should be 0 to 60t. qs is q0 plus f 24t square s by ixx into ds, and t is t here, so this is 1 by t, okay, plus 0 to 48t, t is 1 by 3t here, and I have q2 plus okay. So I get this equation. So all this integral, we can very easily evaluate this integral. So I will get an equation which will help me. So this entire integral equation, this entire equation is going to help me to find the value of q0. I am not solving this entire integration based equation, so which would be very lengthy. So but you should be able to appreciate now that if I solve this equation, we will be able to get the value of q0. So once we get the value of q0, I can plug it in equation 2 to 4, 5, and I can get the value of qs in each portion of the cross section. Okay, so with this I will end this lecture. In the next lecture we will see how to find out the shear center of a closed cross section thin wall beam. Thank you.